My name is Milind Ajay Marathe, and I am currently pursuing my master's from IIT Guwahati. Today, I am going to present my presentation for the deep learning project, whose title is Smart Traffic Flow Prediction and Recommendation System. The goal of the presentation is not to explain just the system, but also how it works internally, from the problem statement to the data set, model architecture, training pipeline, graphical optimization, deployment, evaluation, and the future improvements. So, the traffic congestion is one of the biggest challenges in the urban cities today. Whether it's a daily community, yeah, logistic, or the emergency response, unpredictable traffic can lead to a huge loss in the time, money, and productivity. Our goal is to build a system where we can predict future traffic conditions and recommend the best route before the congestion ever happens. Using the real-world highway sensor data from the Los Angeles, our system employs a spectacle temporal data learning model combining the LSTM network for the temporal learning and the GCN for the spectral learning. This is a hybrid architecture allowing the system to understand both when and where the traffic congestion forms and how it spread across the route. We are integrating the model prediction into a route engine that uses the algorithm like Dijkstra to compute the fastest possible path. And we are using the technologies like PyTorch, NumPy, Pandas, HPy, and as well as the dataset that I'm using is the Meter LA, which is one of the most wide used benchmarks for the traffic forecast research. Now comes the problem statement that means how the foundation is there. Let's study how the data set is there and what it contains. A data set we use is Matter LA is collected from 207 loop sensors placed across the Los Angeles highway. The sensor is recording speed and traffic flow for every 5 minutes. Using this reading, we attempt to forecast time 15 to 16 minutes ahead. But traffic is not random, it has some pattern. For morning and evening peak hours, weekend variation, accidents, rainfall, and many external factors that influence a traffic behavior. To capture this pattern, we have analyzed high congestion areas, peak versus non-peak behavior, missing sensor values, sessional or weekly trends, sensor cluster, and graphical sparsity and connectivity. One of the most important components is the adjacency matrix, which tell us how each sensor is connected to others. Without knowing how road is connected, predicting traffic is impossible because congestion often flow from one area to another. We run connectivity check on the adjacency matrix, counting the nodes, edges, and ensuring the graph truly represents the real world road connectivity. Now the model planning and the architecture strategies. Once the data is understood by us, the next step is this. The first thing we do is define our prediction window. Typically, we take a 12 past timestamps, which is equal to 1 hour historical data. And then we predict the next 3 timestamps, which is equivalent to a 15 minutes. So we first identify the core building blocks of our architecture. Then comes the model. We use the temporal modeling using the LSTM or GRU, where traffic speed over the time from a sequence. LSTM captures how current speed is depending on the previous speed, handling the long-term dependency like gradual build-up of the congestion. Then comes the spectacle model using the GCN, graphic convolutional network. Roads are not independent. One road traffic affects the nearby road. So the GCN help us to learn how congestion propagates across the connected sensors in the graph. This combinedly makes a hybrid spectral temporal architecture, combining both the essential because the traffic has both time-based and the location-based dependency. So we tried multi-model variants. Now the model training. Then now comes the model training. To train accurate model, the data pipeline is critical. The first step is converting the raw continuous sensor reading into a sliding window. For every sequence of input timestamp, we create a corresponding output label. Next, we apply normalization using the min-max scaling because the neural network trains best when the values are consistent range. When we are and then we are splitting the data into different part sets like training and validation and testing set, ensuring that temporal order is preserved and the future data is never leaked into the past. During the training, we use the Atom optimizer, which is a great for sequence data, and MSE laws since we are predicting continuous values. Optional is that we are yeah, that much. And after training, we are evaluating performing using the RMSE exact error distance, and then we have MAE average error magnitude, and there is MAP, that is a percentage error. Together, this metrics give us a strong understanding that the model is forecasting a correct result. Then comes the graphic optimization, means the graph optimization. A core part of this system is a graph optimization, as we have to understand the road network. First, we perform a traffic cluster using the K-mean. We group sensor into region with similar traffic behavior. This cluster helps identify local hotspots and understand which part of the city are most prone to the bottleneck. Next, we optimize the adjacency matrix. Not all connecting or equal importance. Some sensors are strong influence neighboring to one, while others have weaker connection. GCN help us to learn this relationship automatically. Graph model allows us to capture upstream impact when the conjunction is on the one road affects the next, downstream effects, how the traffic clears or worsen the scenarios, and how the propagation pattern, how the bottleneck spreads across the multiple scenarios. Now comes the deployment and the API strategy, where we deploy our model using the RESTless API. This API allow any application, a web dashboard, a mobile app, or navigation system to fetch prediction in real time. Our endpoint provides the prediction speed and the conjunction score and the recommendation of the best route. This architecture makes the system modular. The prediction engine stays on the server while the client application simply requests the update information. This integrates with the traffic dashboards for monitoring, navigation app for the routing, city planner for analyzing the long-term congestion patterns. So this API layer ensures system is scalable and easy accessible. Then comes the route optimization engine. Now that we have predicted the congestion, we will use a particular action to compute the best route. To achieve this, we generate a predicted edge weight. Each road segment has an expected travel time, which has been computed using the predicted time, which is the base distance into the 1 plus predicted congestion. Once we have the updated weight, we will run the shortest path algorithm like Dijkstra, AHR, or any of the algorithms. This step is crucial because even a small prediction congestion increase can significantly affect the travel time. By using the predicted congestion rather than the current congestion, we give the driver a future-aware route, avoiding a road that could have been congested in future. Then comes the model evaluation and some performing metrics. Evaluating this model is an ongoing process. We track various metrics like the RMSE or MAE to measure accuracy of the prediction. But we go beyond just a standard metrics. We also analyze best and worst performing scenarios. Time periods where the model performs expectationally well or it struggles, and the seasonal effect like the weekends or the special event, or it could be a long-term model drift where the performance is slowly degrading. So we also track influence of this latency, which crucial for the real-time system. The faster the prediction, the more responsive the route engine becomes. Now comes the continuous model improvement. Hitting a good accuracy once is not enough. Traffic pattern involves over time. New road constructions, seasonal changes, change work from home patterns, or more anything like that could hit different. So our system include a continuous improvement pipeline. We regularly retain the model using the new traffic law. We tune the hyperparameters like the number of GCN layer, hidden size, or the learning rate. The deployment of the monitoring system detects the anomaly and triggers the automatical retraining if prediction quality drops. This makes the system adaptable, always learning and always improving. So finally, I want to conclude that this smart traffic recommendation system is a complete end-to-end pipeline that learns from the real-world traffic patterns, predict the future congestions, understand the spectrum dependencies, recommending the best possible path. It brings together the whole thing as one and predict the future route that is best possible for you rather than just on the current congestion. That's all.